These are the notes for the 1st of April. That's Tuesday. We're continuing on from where we left off yesterday. So we finished yesterday. We talked about the Young double slit experiment. We're going to start today with a generalization of the double slit experiment. We're going to talk about the diffraction grating. Now, a diffraction grating, it's similar to a double slit apparatus, except that it's got a whole lot more than two. Generally, what you're going to see on a diffraction grating is you're going to see a diffraction grating rated in slits per centimeter or slits per inch. So you end up using the same equations. The same x for maximum is m lambda L over d. But for a dark spot, it's going to be everything that's not m lambda L over d. You're going to get a single spot that's bright at the center, and you're going to get single spots out to the sides, rather than having bright areas with width and dark areas with some width. Now why would this be different? Well, consider light that's 1 centimeter wide. You're going to have 6,000 slits through that centimeter. So if it's not right on a maximum, right on an exact wavelength difference, then your path difference is basically always going to be, then your path difference somewhere in that 6,000, you're going to get one that's exactly out of phase. So, and that's going to be the case for each one of those 6,000. For each one of those 6,000 slits, one of the other ones is going to be exactly out of phase. So you're going to end up getting nothing. You'll get nothing! Absolutely nothing! Of course, if two adjacent slits are a wavelength off in path, then you're good. Then every pair of two adjacent slits is going to be exactly a wavelength off in path. And sehr gut. You get a bright spot. So these will make the fringes with width into points. Why do you think this would be useful? Why do you think this would be useful, especially for, say, astronomers that are trying to find out how far away a star is, using Hubble's law, which basically says the further away a star is, the faster it's moving away from us? So, how do you think that might be useful? Take a moment, think about it. Pause the video here. I'll wait, and when you have a good answer, when you have an idea, start the video back up again, and we'll see if your idea matches the physical principle. Okay, we're back. So this will help us because we know what spectra. We know the emission and absorption spectra for the elements. So when we see, say, the hydrogen spectrum, but it's all shifted a certain distance away, that lets us know, okay, we know exactly what wavelength we're seeing, and we know what the wavelength should be. If we have fringes, we might not be able to measure exactly where the brightest spot is, exactly where the center is, but with the diffraction grating, doesn't matter. We don't have to measure exactly where the center is. It takes all the guesswork out of it. Say, okay, I have points here, 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 and here. So that tells me exactly what the incoming wavelength is. So that's where it's very useful for astronomers. Diffraction gratings we're really just going to cover conceptually, and we're now going to get into reflection and refraction, which is something that we're going to talk conceptually about today. We're only going to get it conceptual today, with one exception. We're going to talk a little more about reflection, but we're really going to get into refraction tomorrow, because we're going to have another piece of the puzzle that's going to make us able to do calculations for refraction, and that's going to make things a lot more useful. So, reflection. Do we all remember the old saying, the angle of incidence is equal to the angle of reflection? I hope so, because it's true. Every angle for reflection and refraction problems is measured from the perpendicular, which is called the normal. This is an important term, normal to a surface. Remember the normal force, the force perpendicular to the surface? Well, we measure our angles from the normal line, the line perpendicular to the surface. I have light incoming into a surface at some angle with the perpendicular, some angle with the normal. It's going to reflect off at that same angle. That's a very powerful and very helpful tool. Now, we're also going to have light get refracted or bent by a material when it goes into the material. We use Snell's law, S-N-E-L-L'(S). Snell's law will tell us about the direction of refraction. And we'll get into that tomorrow, because we really need to talk about index of refraction before we get any further into Snell's law. But for the purposes of reflection, use the angle of incidence equals the angle of reflection. Measure the angle that it's coming in away from the normal, and it's going to come out at the same angle. So I have this. So there's a problem at the end. There's a problem at the end of Note Guide 4.1, Note Guide April 1st, that talks about light incident on a surface at a 75-degree angle. It's going to reflect off of that surface at what angle? Think about it, and then my eyes are 193 centimeters above the ground, which is approximately the case. I mean, it may be a little less than that, but for these purposes, we're going to call it 173 or 193 rather. How far away from that point do I need to stand to have the light shining right in my eyes, to have the light reflecting off of that surface right into my eyes? Think about it. Do the trig. I want you to actually do the trig, just like I want you to actually do the trig from yesterday. I'd like you to do the trig for yourself and see that those equations are right. Don't just take my word for it. Do the trig. That's about all I want to get into today. Today is just a conceptual day. Tomorrow is going to be some meat, though. We're going to have some nice meat on. We have some real nice meat out of index of refraction and Snell's law for tomorrow. Have a good day. Don't make trouble for Miss Swihart. She's going to leave me a note. She's going to tell me exactly who's given trouble, and you don't want it. Just trust me. You know I'm easygoing about things, but you also know that I don't put up with stuff. Have a good day, and I'll see you guys on Thursday, and you'll see me again tomorrow with more video lecture.